Thank goodness, Kylie, you asked. I got one that's not too bad today. And now, Ryan and Alan, it's going to be on the video. Oh no, I could get in trouble. I could be bad. Okay, let me, I'm on the wrong page here. Hey, those of you that are at home, can you guys see that? Carson, can you see that?
Yes.
Good, okay, perfect. Okay, so quick review. So, and I will do jokes, Kylie and Ryan and Alan and everybody at home. I know you guys want jokes. I want jokes. But I forgot jokes, Alex, in our class.
Oh, yeah, you did.
Well, it's good you're here because now you're going to get them. But what we're talking about is a chapter on equilibrium. And like I told you, in previous years, in the springtime in regular chem, we would have done a significant amount of what we're going to be doing back then. And but thus I need to slow down a little bit. But first of all, we said, okay, what is equilibrium? And we said equilibrium is when the rate of the forward reaction equals the rate of the backward reaction. And that's why we get a double arrow. Like you can see, we're going to work with these equations today. I'm pointing to equations on the board. You'll see a double arrow. So that's telling the reader, the chemistry reader, that this reaction is, the reactants are reacting and making the products, but the products are reacting and making the reactants as well. So that's what equilibrium is. And then there's this weird thing that I talked about yesterday, and the key thing on this slide was the far right-hand column. And if you take a ratio of the products on the top, and their exponent is the coefficient, and the reactants on the bottom, and today actually that's the first thing we're going to work on, is simply writing this expression, you get a constant number. And if you look over on the far right-hand side, fairly constant number. That's why they call this the equilibrium constant. So it's fairly a simple, straightforward thing. And we're just going to, the first thing we always got to do is write the expression. So the products will go on top, the reactants will go on the bottom. And you get this equilibrium constant. And this is on our formula sheet. And so we were working for a couple weeks on kinetics down here. We're now working on equilibrium. And we'll talk today about the difference between Kc and K2. So they call it the equilibrium constant because it always gives the same numerical value. Okay, and then I put up some of this yesterday, but I didn't put up all of this. So let me put this up, and then we're going to come back. But thanks to Kylie, Alex is here. Jokes. Thank goodness. I'd forgotten. I got so busy with other stuff. Okay. Oh, here's a great chemistry joke. Brian will be glad you're back. A white bear and a black bear, they both jump into a river. Which bear dissolves? The white bear, because it's polar. Mike, he doesn't want to give me eye contact on that one. Okay. I'm not a Catholic person myself, but I highly admire people of the Catholic faith. And people of the Catholic faith, some of you might be Catholic people, you guys do this really cool thing. I think it's really cool. It's like you cross yourself. Well, this is a joke, okay? And everybody knows me that, Jesus is most important to me. And, I don't want to make light of it, but it's just a joke, okay? So Catholic people are really, really glad that Jesus died on the cross. I am too, because thank goodness for that. He took care of all my problems and my mistakes. He paid the price for them. But Catholic people are really glad he died on the cross because they did that. Because if he had been stoned to death, which was another means of killing people, you know what Catholic people would have to do? Okay, last one. Alan, are these jokes registering at all? Okay, I saved the best to last, I think. Maybe not. Okay. These two old duffers, two old men, are sitting in a nursing home doing whatever old men do, which is probably talk about the stock market, wondering, are the Rockies going to lose 100 games, like just be terrible, they're awful, or the Nuggets, they're doing good, or how politics and talking about all this. These two old duffers, we'll just call them Fred and Barney. And out of nowhere, this elderly lady streaks by them. Now, Luke, you know what streaking is, right? It's running around in your birthday suit. So this elderly lady streaks by him. And so here are these two old duffers talking about whatever old duffers talk about. And their jaws drop. This elderly lady streaked by them. And Fred went to Barney, goes, what in tarnation was that? Barney said, I don't know, but whatever it was sure needed to be ironed. That's it. That's all I got. I thought it was pretty good. I guess we kind of wrinkled, I guess. Kylie, was it worth asking, even though you didn't ask?
Yeah.
I thought it was pretty good.
That was the one for this recording.
I kind of drug it out there a little bit, didn't I? Okay, so let me give you guys a second again to write these. So what we're going to do first, and we're going to get a little bit into numbers, but before we do that, we're just simply going to, again, because we didn't do this at the end of last year, and if you had been in a normal year, you'd say, oh, yeah, I remember doing those. Those were easy. I remember how to do those. But and they are easy, and you'll pick them up fairly quickly. But then we're going to so first of all, we're going to work on writing the equation or writing the expression. And then we're going to get to where we're going to start plugging in numbers. And then we're going to start next week. We're really going to ratchet it up a little bit. We're going to go to ice tables. Do you remember ice tables? And again, that was one thing in spring that we really would have introduced. And of course, last year was so weird, but we're going to work on those. And we're actually going to come down to the quadratic equation, which is like, but I will tell you there's nothing that's going to be required, the quadratic equation, but I am going to give you a chance for some extra credit. Okay, so just reading on the top, number one, liquid solutions express concentration in molarity, which is going to be the case most of the time. And gases express concentration, molarity, or atmosphere. So Kc is when we're using just molarity. Kp is when we are just looking at gases, and that's where we'll be talking about pressures. And that is not going to happen as often, but again, not something that's a hard thing to distinguish. We do Kc and Kp, the way we write out the equation or the expression is exactly the same. Solids and pure liquids are not included in the equilibrium expression. I always use this as the example. So if you were asked the question, what is the molarity of pure water? What's the molarity of pure water? Well, this is pure water, we know, is 1,000 grams, and it would be a volume of 1,000 mils, because we know the density of water is 1 gram per 1 mil. So again, the question I posed here was, what is the molarity of pure water? Well, remember, molarity is moles per liter. Moles per liter. So if I have 1,000 milliliters, that means I have 1 liter. So that's what's going to go on the bottom. So again, what I'm trying to do here is I'm trying to find the molarity of pure water. And then if I have 1,000 grams, and I want to get that into moles, so water is 18 grams for 1 mole. That's 55.6. Okay, so I'll take that then, and I'll put it here. And so the molarity of pure water is 55.6. And the point of this, the point of doing this, even though it's kind of cool, you can now determine the molarity of pure water. But it is always that. It is always that. It doesn't change. And that's why point 2, it says solids and pure liquids are not included in the equilibrium expression because their concentration never changes. They never change. So what I always tell students in first year chem, when you see a solid or a liquid and you're writing these K expressions, these equilibrium constant expressions, just write 1 in their place. And really, The only time you really have to write in 1 is if you just have a solid or liquid is the only thing on the right side on the product side of the equation. So the reason I did this was to make the point that water is always going to have a molarity of 55.6 molarity. Point is solids and liquids concentrations never change. And so their value is included in the K expression. So solids and liquids are not included, or just write 1 in their place. And then I've done, so if you look at letter A, the equation, so CaF2, double arrow to Ca plus 2 plus 2F negative. All we're doing right now is we're just writing the expression. And notice Kc is equal to the Ca plus 2 aqueous and the F negative 1 squared. But the solid, I didn't include it, because solids and liquids have an unchanging concentration. If you had written it over 1, like I said, tell my first year chem students, if you have a solid or liquid, you write in 1, that's okay. But mathematically, that doesn't change anything. If you look at B, so we have CaCO3 solid. So again, I'm not going to include that. Double arrow with CaO solid, so that's going to be 1. Makes CO2, so then the Kc is just equal to the CO2. So the CaCO3 and the CaO must be present in order for equilibrium to be achieved. The concentration of a solid, just like I'm making the point, the concentration of a solid doesn't change as the reaction proceeds. Okay, so let's just simplify this. This is really not that complicated, and we're going to do some examples. So I've got some written on the board. I'm going to do a couple, and I'll have you guys do a couple. But all we're doing, step 1, is we're just writing out the equilibrium constant expression. So what we do is the products go on the top, the reactants go on the bottom. Okay, so the products on the top, the reactants on the bottom. Number 2 is the coefficients become the exponents. And that's why I made a big deal, if you remember, we were talking in chapter 12 about the lowercase k, the rate constant. That's different than this. I said we didn't do that. We didn't take the coefficients to find the exponents. We kind of did at the very end of the chapter when we were doing reaction mechanisms, but we found out the exponents by those ratios from the concentration rate data. Okay, so products on top, reactants on the bottom, number 1. The coefficients become the exponents too. And if you have a solid or a liquid, they're just 1 or they're not included. Okay, so I have a bunch of reactions. So this reaction here, we can write it in terms of Kc, concentration, or Kp. And I'll show you, they're really the same thing. So what's on the right goes on the top. So I have NaCl, and it's squared. And the reason it's squared is because the coefficient is 2. And then what's on the left goes on the bottom. So I have NO, and its coefficient is 2, and Cl2 to the first. And in first year chem, for you guys, this isn't, again, I just want to make sure we know what we're doing here, because this will be the foundation. We got to be able to write these expressions. But little things you got to be careful of. Again, right? What's on the right on the top, what's on the left on the bottom. The coefficients become the exponents. But notice in the chemical equation, it's NO plus Cl2. But in the K expression, you don't have plus, you multiply. Okay, so if I write this in terms of Kp, this would just be pressure. So I'd have the pressure of NaCl, which would probably be in ATMs. I do it exactly the same way. Kp or Kc. The thing with Kc is it's brackets. And remember, brackets mean molarity, where here it's pressure. So then I have the pressure of NO squared and the pressure of Cl2. Okay, so let me, okay, I'm going to move my computer over here and just make sure those of you at home, can you guys see my hand?
Yeah.
Okay, so for reaction 2, so this one, so really to simplify this.
Wait, Mr. Wood, do you mind? Mr. Wood, do you mind lifting the camera up a little bit?
Thank you, Rex. Is that better?
Yep.
Okay. Is that really all that's included in the K expression are aqueous and gas. That's it. Solids and liquids are not. Aqueous and gas. If it's aqueous, it's got to be Kc. So here, so I have what's on the right on the top. So I have Ag NH3 squared plus B to the first. Okay, and then what's on the left would go on the bottom. So I'd have Ag to the first and then H3 squared. And the reason it's squared is the coefficient was 2. So the coefficients become the exponents. The subscripts here just go right in the parentheses. Okay, so for number 3, then, so again, this has to be Kc. Kp can only be for gases. So I have Cu positive 3 to the first. And then a solid, which again, you really don't even have to write in 1. Solid would be 1. What would the left, or what would the bottom look like? What would the denominator look like? Anything in the denominator? Brian?
Would it be the AG to the third?
To the third. Very good. Ag plus 1 to the third. And then again, the solids, again, you really didn't have to include those. Again, not too complicated. So what's on the right on the top, what's on the left on the bottom, the coefficients become the exponents, and all that's included are gases and aqueous, not solids and liquids. Try number 4. Let's do it. Just do it first of all in Kc. We can also do Kp. All we're doing here is we're just writing out the expression. So I have a solid, which again, I'm just showing you that I always write in 1, but you really didn't have to. Another solid. Not too bad, right? Not too bad at all. So if we do Kp, it's still the exact same process. We're just doing it in terms of pressures. So I would have the pressure of H2 to the 4th. And again, the solid, same thing. It's exactly the same thing. And then the pressure of H2O. Okay, so again, but this is always going to be the first step in just making sure we're good with that before we move on. So, okay, and here's a couple, again, just because this is an important concept, the next slide is going to show you the same thing. So here is a couple more written out. The top reaction, letter C, is acetic acid. And again, when I see that, I immediately comes up that we have talked a little bit about acids and bases, but acids and bases are a huge thing in AP chemistry. And this is one of the topics that we've got to get to at least a little bit after spring break. Actually, chapter 14 and 15 together, both about acids and bases. And at least get through, I don't know, I've got to figure it out. But that's acetic acid. But notice how the Kc is written. And that's the point right now. So you get what's on the right. So acetate ion, hydronium ion, and then acetic acid. But the H2O liquid, because it's a liquid, remember, solids and liquids are not included. So writing in a 1 doesn't really affect anything at all. So the solvent water changes concentration only minimally, so we ignore it because it's, again, liquids and solids are ignored. Therefore, it's excluded from the expression. So if you look at this one, this is a reaction, too, for a lab that, again, because I still want to do some labs, but I've got a solid, solid, liquid, so they're not included. So all I have, Kc, is just CO2. And Kp, because it's a gas, when it's a gas, you could write it as either Kc or Kp. When it's aqueous, it has to be written. It has to be written in terms of Kc when it's aqueous. Okay, so first basic thing here is just writing out the expression. And again, in first year chem, we spent just again pretty much a regular 50-minute lesson just on making sure we were good, what equilibrium was, and writing those out. And again, for you guys, hopefully that's nothing that is too bad. Okay, now I want to get into how K changes if you change the equation. In other words, and we did this back in the fall with delta H, but if we double the coefficients, how that changes K. We'll talk about how we did it with delta H. If we reverse the reaction, how that changes the K values. So that's what this slide is about. Okay, so I'm going to leave that up here, and I'm going to go back and I want to review, but let me, for those that are taking notes, and this will be something that definitely is going to come up here. This is different than what we did with delta H. So I want to compare what we did with delta H and what we do with K. Alex, it was so lucky you were here. You got to hear the jokes. So if you look at this, first of all, look again how K was written. So here's KC1, or just this reaction. So again, what was on the top, the H2O gas went on top. And then what's on the left, the H2 and the O2 go on the bottom. And then the coefficient determines the exponent. So I got the half was the half exponent on O2 was because the coefficient was half on O2. So that's what we were just working. But the point here is what you do with when we double the coefficients. If you remember delta H. When we double the coefficients, like here in the second reaction, do you remember what we did to delta H? We doubled it. Somebody said it. We doubled it. Here it's different. Here we square it. With K, we square it. I'm going to just do a quick, for my own sake, just a quick inventory of comparing K to delta H. But here we square it. So where there's those 3 question marks, I'm going to take that, and that is a big number, 5.8 times 10 to the 40th. And I'm going to square it. And so where those question marks are, what we should have there is 3.4 times 10 to the 81st. That is a huge number, which means that is really going to the right. Okay, then look at number 4. So if the reaction is written in reverse. So if you remember what we did with delta H, do you remember what we did with delta H when we reversed the reaction? We changed the sign. Very good, Brian. Here we take the reciprocal. So on number 4, where there's the 3 question marks, we take the reciprocal. So we take 1 over 5.8 times 10 to the 40th. And this is going to give me an incredibly small number. We do 1 divided by 5.8 gives me 1.7 times 10 to the negative 40. Okay, so just a quick summary. This isn't in the notes, but this might be worth noting. But we're going to compare KC to delta H. So if I have the KC and I have delta H, oops. Okay, so if we take the coefficients and we double them, with delta H we would have doubled. With KC we would square. Different. If we reverse the reaction with delta H, what we did back in the fall is we flipped the sign. And to me, because we're talking about getting the Princeton review, we're talking about starting review. Well, this is something that, for me, has always been kind of confusing. We actually do something in Chapter 17 with this thing called E0, and some of the things are a little bit different here. We switch reactions, and I'll go back and I'll summarize it again. Here you take the reciprocal. Okay, and then if you cut it half with the delta H, you would cut the value for delta H in half, but here you would raise to the 1/2. So what we do with K is different than what we did with delta H, and that's important to note. Okay, and that will come up once in a while. Okay, so here we go. The magnitude, well, what does the K mean? Okay, so we talked about, okay, what is equilibrium? And then there's this weird thing that happens at equilibrium where the products over the reactants, the coefficients become the exponents. Don't include solids or liquids, you get a constant number. Well, what does it mean? Well, if you think about it, K is equal to the products over the reactants. Well, if K is large, and I'm going to talk about large here in just a couple of minutes, but if K is large, that means the number in the numerator is greater than the number in the denominator. That makes sense to me. So if K is large, then there's more products than reactants. And if K is small, and I'll talk about what I mean by small here in a minute, well, that would mean the number in the denominator is smaller than the number in the numerator. So the reactants would be greater than the products. Okay, so in this case here, so in this reaction, 2O3 in equilibrium. So here's ozone combining to make oxygen. So again, write K, so the products on the top, the reactants on the bottom, a large number, 2.454 times 10 to the 12th. It sounds like how many games the Rockies are going to lose this year. Large number. But in this case then, because K is large, the product value, the O2, is greater than the O2, or the O3, the reactant. So equilibrium favors the products. And Alex, just staple your work to your actual test and put it up. Okay, so here now is the first example of a problem that has some numbers to it. Okay, so, and again, in first year camp, we would have spent a day doing problems like this, and we're going to do a couple of them here today. Oops. So calculate the ozone. Ozone is O3. So here, it is truly just plug and shove. So I have the K value. I was given the O2 value, and the O3 value is X. Okay, take a second, solve for X. And again, the thing you just gotta, not that it's hard, you just have to be careful. You just have to not be careless and forget to square or cube or so on. So I rearrange the equation. And then again, you got to remember to cube, but if it's square root, you got to take the square root of that. And again, it would be a good practice just to do that on your calculator. So here we're finding the concentration, which is molar. Did anybody try this? Did you get that right? And again, and I haven't made enough of, I haven't done a very good job of whenever we do a calculation, it's always kind of good to step back and go, okay, does that make sense? With a K value that is that large, 10 to the 12, and I get this number, that large K tells me there's a lot of products and a little reactants. So if my products are 0.5, that does make sense. That would be really small. Okay, and then here's a reaction where the K value is really small. And I'm going to talk about small and large here in a second. So in this case, the denominator would be much larger than the numerator. The next slide, I'm going to talk about small numbers and big numbers and kind of to give boundaries on those. But 10 to the negative 38th is a very small number. Okay, a little bit more. Okay, so here's another problem. Okay, I'm going to go ahead and give you guys a minute and see if you can do it. Here's another reaction. Neither large or small K. And before I want to talk about that bluish red arrow there. See if you can solve for K there. Or not K, I'm sorry. See if you can determine CO2. So go ahead and read that. Let's just take a minute here, see if you can do this one. Again, in first year Chem, you spend a day probably, one writing the expression, and then another day just giving the values, plugging the numbers in. So now I have the equation. Now I'm just plugging in numbers. That's why writing out the equation first is important. And again, I think for you guys, pretty simple algebra. What I get for the CO2, which is X, is 1.4. The unit on that would be molarity. Did anybody else get 1.4? And then again, okay, does that number make sense? Well, K is, again, not really too big or small there. But it's bigger than 1, so we would expect a little bit more of the products and the reactions. I'm actually a little bit surprised it's a little bit that big, but that would be on the side I would have expected it to be on. Okay, and then if you look at this this arrow, very small and very large, what you should note from this. So I'm looking right there in the middle of the page, very small, very, very large. It kind of goes, this is the way chemistry defines it, from 10 to the negative third, or 0.001, to 1,000. And that's where they're kind of equal. So from 1,000th to 1,000, fairly equal, the products and the reactants. But less than 1,000, would favor more reactants and products, more in the denominator than the numerator. And greater than 1,000 would favor more products and reactants. So again, kind of the boundary, okay, where things are fairly close to equal. What they say in chemistry is from 1,000th to 1,000, fairly equal. But less than 1,000th, this is the value for K, less than 1,000th would mean there's more reactants and products, and greater than 1,000 would mean more products and reactants. And then just here on the bottom of the page, just vocabulary, homogeneous, like I think of homogenized milk, are where all the reacting species are the same phase. So everything is in the same phase. Heterogeneous, like I think a heterogeneous mixture, not the same throughout. The reactants and the products are in different phases. So kind of makes sense, the vocabulary there. Okay, and I'm almost done. I want to just talk about the beginning of the next slide. Now again, tomorrow we will not Google Meet, but I will post like a 15-minute video lesson that you guys can watch, and it's going to be about the beginning of this next slide. Okay, so this now, what this is, and this is actually something that is not on the formula sheet. And so, but I always include this on the quiz for chapter 13 and the test. So I'll write it on the board. If you want to write it on your formula sheet right there where it says equilibrium, you can. I'm not going to tell you can't. I don't think it's going to be on the AP test. I think if it was on the AP test, they'd give it to you. And so I think if they were to give it to you, they'd write it in the problem. That's why on the day of whenever that day is of the 12-13 test, I'll write this equation on the board. So nothing to memorize, but you do need to be able to use it. So this is the connection between KP and KC. And this is actually for tomorrow's lesson. I'm going to do some problems with this. And one thing I haven't made a point of, and I should have, and I will as we go through the next week, but the units on K, all year long, I've tried to make a huge thing about units. And you guys have done a great job of asking questions about that. K is something that has no units. And I think actually if you go down that engineering path or medical path or chemistry or physics path in college, I think about your junior year, they start to have units with K. K is a ratio to me. It's a ratio of products to reactants. So for us, K is one of the rare numbers without a unit. But KP is equal to Kc. And notice how this works. Parentheses RT. And the value for R is a 0.0821. Remember, R had a couple different values. And the temperature has to be in Kelvin, raised to the delta N. And to me, when I did this, and I went over this morning myself, but it's the moles of the gas. It's all that matters here is the gas. So you take the moles of the gaseous product minus the moles of the gaseous reactant. So it's the gas product minus the gas reactant. Okay, and last thing, and then again, I'll pick up here tomorrow. But think of this mathematically. When would Kc equal Kp? Look at that mathematically. And again, I made the mistake so many times, I think I finally remembered to remember that it's parentheses RT raised to the delta N. So the delta N goes to the RT. So mathematicians, when would Kc equal Kp? Not when Kc is 0. Right?
When the moles of the gaseous product equals moles of the gaseous
Right.
reactant. So
When delta N is 0, right? When delta N is 0, then anything raised to the 0 would be 1. So the answer to that question, when the moles, just exactly what Ryan said, she was exactly right. When the moles of the gaseous product equal the moles of the gaseous reactant. Okay, I'm stopping there. Okay, so those of you at home, you guys, if you want to stay on, I'm more than happy to answer any questions you have. I do want to take a minute and answer these guys' questions first. But, and if you guys want to head out and get an early lunch, you feel free to do that. And again, no Google Meet tomorrow. So if you guys are over and out, and if you want to hang in there, you can. I'll see you guys Monday.
Have a good
Thank
one.
Mr. Wood.
Thank
you, Mr.
Thank you.